Good afternoon, my name is Maya and I'm here to represent my colleagues, Mr. Nugroho Adisasongko and Mr. Nujaman Putra. We are from the Research Center of Sustainable Production System and Life Cycle Assessment from National Research and Innovation Agency, or BRIN. We want to take this opportunity to thank you for allowing us to come to ICGAB2022 to present our research. Our topic is Review of Types of Biomass as a Fuel, Combustion Feedstock and Their Characteristics. We're here afternoon to talk to you about agricultural issues that we feel can be utilized another purpose. And this is our explanation. This is content of our presentation. First, introduction to our topic. Biomass is organic matter produced through photosynthetic process, whether in the form of product or waste. In addition of being used for primary purpose of fiber foodstuffs, animal feed, vegetable oils, building material, and so on, biomass is also used as a source of energy. Utilization of waste as fuel gives three direct advantages. First, an increase in overall energy efficiency, because the energy content contained waste is quite large and will be waste if not utilized. Second, cost savings, because often disposing of waste can be more expensive than utilizing it. Third, reduce the need for landfills, because the provision of landfills will become more difficult and expensive, especially in urban areas. Next, environmental aspect. The use of biomass as a fuel is more environmentally friendly than fossil fuel. The following are the contributions of biomass utilization to improve environmental quality. Next, method. The development of biomass utilization of energy in the future is the combustion of biomass together in existing coal boiler and the introduction of high-efficiency combined cycle gasification system, fuel cell system, and modular systems. Biomass utilization technology for energy or energy reserve based on the system, direct burning, joint burning, gasification. Next, the material of biomass that used in the study is three, which are rice husks, ironwood sawdust, and the thick sawdust. The three of this biomass is compared with the coal as the main fuel in the and the CFPP or coal-fired power plant. First, rice husk. The husk in the part of grain in the form of dry, scaly, inedible seed. Agricultural waste such as rice husk can be used as an environmentally friendly and economical energy source, but until now rice husks have not been optimally utilized as an energy source. The heat value contained in the rice husk is quite large, which is about 40,000 kilocalories per kilogram, equivalent to 4.52 kilowatt hours. The table shows what characteristics of rice husks from research by Mr. Sumartono. Next is sawdust. Wood sawdust waste causes many problems in handling and has not been used optimally. The waste is left to rot is burned by sawmills or wood craftsmen. Mixing sawdust and low calorific value coal with a curtain ratio can be an alternative to increasing the utilization of sawdust and low calorie coal at the same time. The chemical content of wood is shown at the table from previous research. Research method. The picture shown was a biomass testing. Material characteristics have been tested, which was carried out in the laboratory. To determine the content and properties related to the characteristic of the power plant, Figure 2 shows the activity testing of the characters of materials, namely rice husk, ironwood sawdust, thick sawdust, and coal. The next is result and discussion. First, coal testing. The result of coal testing using the STM method are shown in table 4 below. The test results show that the gross calorific value of coal or HHV of 5,217 kilocalories per kilogram with a moisture content of 11.43% and S of 8.36%. The relative density of coal is 1.412 gram per milliliter. Next is rice husk testing. The result of rice husk testing using the STM method are shown in table 5 below. The test results show that the gross calorific value of rice husk is 3,380 kilocalories per kilogram, is smaller than coal, while the moisture content of 6.84% is less than coal. The S content of 21.4% is much greater than coal. The volatile matter content, which is 59%, about 10% higher than the coal, and fixed carbon of 11.71%, much lower than the coal. Next is ironwood sawdust testing. The test result of sawdust ironwood using the STM method are shown in table 6 below. The test results show that the gross calorific value of ironwood sawdust is 4,465 kilocalories per kilogram, lower than the coal but higher than the rice husk. While the moisture content of 7.74% is less than the coal but higher than the rice husk, the S content of 0.96% is much lower than the coal and the rice husk, while the volatile matter content reaches 71% is much higher than the coal and the rice husk. However, the fixed carbon content is 20%, is higher than the rice husk, although lower than coal. Next, thick sawdust testing. The result of thick sawdust testing using the STM method are shown in table 7 below. The test results show that the gross calorific value of thick sawdust HHV is 4,460 kilocalories per kilogram, approximately the same as sawdust ironwood, lower than coal but higher than rice husk, while the moisture content is 5.26% is less than the coal rice husk sawdust ironwood. The S content of 2.69% is lower than the coal rice husk but slightly higher than the sawdust of ironwood, almost same as ironwood. The volatile matter content of thick wood reaches 75%, much higher than the coal rice husk, but is slightly higher than the ironwood. However, the fixed carbon content is 15% is lower than coal and ironwood, but higher than rice husk. Next is analysis of biomass feeding system. Things to consider in the biomass feeding system into the boiler, especially for CFB type boilers, including first density and particle size. The density, together with the particle size, actually determines the fluidization character of the biomass material to the mixed materials. With a low density, tend to be more easily carried by the air than the coal. With the same air velocity, biomass particles which have density smaller than biomass are possible to be carried higher and burn at a different location than the coal, and cause different temperature distribution in the combustion chamber. Therefore, one of the requirements that must be met in the mixing biomass is minimal density. If the minimum density is not met, it should be considered to first process of the biomass particle used into pellet to achieve the minimum density requirement. The following table the density of coal, rice husk, ironwood, sawdust, and thick sawdust. It can be seen from the table 8 that although the relative density of rice husk is higher than coal, the bulk density is very low. In the condition of biomass supply, as it is, rice husk has a lighter density than a coal or sawdust. For these reasons, it is necessary to consider the feeding system of rice husk in the boiler, taking into account of flying characteristic of the rice husk. For mixing up less than 5% by weight of fuel, it's estimated that there is no serious problem with mixing rice husk because all rice husk will burn out in the combustion chamber. For larger quantities, it is necessary is consider converting them into pellets to increase the density close to that coal, so that they approach the flying characteristics of coal and more manageable to burn out in the combustion chamber. For sawdust with a higher density, it is easier to regulate the airflow to keep it burn out in the combustion chamber up to higher biomass ratio. The next is conclusion. From the test result of the characteristic of fuel to be used for biomass co-firing at the power plant in the form of coal, rice husk, ironwood, sawdust, and thick sawdust can be concluded as follows. The value of coal, rice husk, thick wood, and ironwood calorific value, volatile matter content, fixed carbon, moisture, and S is shown as below. The bulk density of biomass is lower than coal, especially rice husk, which is only 0.11 kg per liter, needs special attention in its preparation so that it can be mixed well with coal and can burn out in the combustion chamber under the same fluidization condition as coal, especially when mixed in a portion greater than 5%. That's all our presentation. Thank you for your attention. Good afternoon.